Well, good morning. This is Thursday, the 28th of February, last day of February, 2019, 11:37. We're 7 minutes late getting started for a linear algebra class, and right now I'm still the only one in the classroom. I've been waiting to see if someone else would show up. So far, nobody has shown, so I'll go on and get started without you. But whenever you come in, you'll have to just pick up where we are. But it will be recorded for later reference. So let's start with the current slide. And I get my pen situated. Okay. Now, where we left off last time, Chapter 2, Matrices, 2.3, Inverse of a Matrix, we were just getting ready to do the rules. We had led everything up to the rule, but let's now write the rule down. Okay? For some reason, the pen didn't take. Okay, there. I think it did. I hope it did anyway. Yep. Okay. Finding the inverse of a matrix by Gauss-Jordan elimination. I'm just going to shorten this by Gauss-Jordan elimination. Now, notice here, Gauss is no longer just an option here. It has to be Gauss-Jordan. Okay? That means you find that leading one, get all the zeros below it and all the zeros above it. Okay? Has to do that in order to get this done. All right? Now, before you even begin, if you're trying to find the inverse of a matrix, if that matrix A is not square, hang it up. There is no inverse for a non-square matrix. So A has to be a square matrix, and we'll call it of order n. In other words, an n by n matrix. Okay? So, once you have that, first step. Write now a n by 2n matrix. Okay, what is that? Well, the n part is your n by n A. So this will be matrix A. Adjoin, that's not the right word for it, augment that, or adjoin that, actually adjoin was right, with the identity matrix of size n. That gives you your n by 2n. Still have n rows. You had n rows in A, you have n rows in I. Write them adjoining each other. So now we have the n columns of A plus the n columns of I, which makes it a 2n matrix. Okay? With matrix A on the left and the n by n identity matrix I on the right to obtain, and they refer to it this way, AI. That's not artificial intelligence, by the way. Okay? That process is called adjoining the matrix I to the matrix A. Okay? Number 2. Once you've done that, if possible, row reduce this thing, starting with the A's there on the left, to the I matrix. Row reduce A to get it to become the I matrix. Okay? Now, if you can't get it to become the I matrix, that means there is not a invertible matrix. The A does not have an inverse. If A does have an inverse, then you can reduce it to the I matrix. But while you're doing that row reduction, you're also operating on the I here, doing those same operations on I, and what you wind up with, the I has moved from I to become A inverse. Okay, I jumped ahead. Sorry about that. No, they did it here. Result will be the matrix I A inverse. So this will be the new matrix. A became I became A inverse. Okay? If that's not possible, then A is non-invertible, or another word for it is singular. Now, check your work. This is the third step, and this is always a lot of fun. Check your work by making sure that A times A inverse is equal to I, and also that A inverse times A is equal to I. Now, that sometimes takes longer than the rest of them put together, but you can still do it. Now, here's at the bottom of this section, this page, is another linear algebra applied he does a pretty good job of putting these in most sections. Recall Hooke's law, which states that for relatively small deformations of an elastic object, the amount of deflection is directly proportional to the force causing the deformation. A simply supported elastic beam subjected to multiple forces of the direction D is related to the force W by the matrix D is equal to F times W. Okay, now, really don't like that. I guess this is the way they refer to it, but you see, F is a flexibility matrix whose entries depend on the material of the beam. The inverse of the flexibility matrix, F inverse, is called the stiffness matrix, as opposed to flexible matrix. And they'll talk about those in exercises 61 and 62. So what I don't like about it is capital F in physics is usually reserved for the force, and yet they made the force the W vector here, which is just it's just terminology, okay? But the deal is that the D and W here, I think are just vectors, excuse me, not matrices. I don't see that they do, and usually when they put a bold, that means a vector, okay? So that's just at the bottom, but just another application of linear algebra. And if any of these really strike a note with you, a chord, you know, that makes you feel warm and fuzzy, by all means, follow them up and see if you can get a paper out of them. Which means, please get working on your papers, folks. Need those before the end of the term. Okay, so let's go to example 3. Here's a matrix A. And this matrix A is a 3 by 3, 1, minus 1, 0, 1, 0, negative 1, and negative 6, 2, 3. Okay, that's matrix A. It says find the inverse of that. So rather than write it down and do a couple things, what I'm going to do is just go on and adjoin this with its appropriate identity matrix, which is a 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, now, what do you want to happen? So this is now no longer just A, this is A, I. Okay, now, what do you want to happen? You want that upper left entry to be a 1. Guess what? It already is. We don't have to do a thing to make it become a 1. So we're happy. We go on to the next step. What do we want next? We want the entry under that to be a 0. Well, how do we get that? Minus row 1 plus row 2. That's going to make that become a 0. So you do it to the entire row. Now, since we're using row 1, just write it down. 1 minus 1, 0, 1, 0, 0. Okay? Now, we're operating on row 2 with row 1. Minus row 1 plus row 2, minus 1 plus 1 is 0. Plus 1 plus 0 is 1. Oh, nice. Minus 0 minus 1 is minus 1. Minus 1 plus 0 is minus 1. Minus 0 plus 1 is 1. And minus 0 plus 0 is 0. Okay, hope I did it right. Just a good old Gauss-Jordan row reduction like we have done before. Okay, what you want to happen next is that minus 6 to become a 0. How do we get that to happen? Multiply row 1, that's the row we're using to do this, by 6. So 6 row 1 added to row 3. And that's going to be the new row 3. So 6 times 1 is 6, minus 6 is 0. 6 times minus 1 is minus 6, plus 4 is negative, plus 2 is negative 4. I'm doing my addition in my head. 6 times 0 is 0, plus 3 is 3. 6 times 1 is 6, plus 0 is 6. 6 times 0 is 0, plus 0 is 0. And 6 times 0 is 0, plus 1 is 1. Okay. Sorry. I had hoped to be able to take a little break between my two classes and get something to eat or drink, because I've been going solid at it since 8:30 this morning, actually, before that. But I didn't have a chance because I gave a test in my first class, and so at the end of my second class, I had two students, one from this afternoon's class and one from this morning's class, that needed to work on making up tests, so I had to get them set up, and so I had 0 time to even stop and get anything to drink. So I may have to pause at some point here just to go get something to drink, because my throat is very dry, but I'm going to try to truck on here that I can. So we got a 1 here, 0's below. Go to the second row, you want the first non-zero entry to be a 1. There it is. So we don't have to do a thing to get it. But we want the entries both above and below to be zeros, so therefore we're doing Gauss-Jordan elimination, so we need to get that -1 above it to be a 0, and that's pretty simple. Just add row 2 to row 1, and that will give you a new row 1. So this becomes, we're using row 2, which is 0, 1, -1, -1, 1, 0. Pretty symmetric seeming, isn't it? And add to that row 1. Okay, 0 plus 1 is 1. -1 plus 1 is 0. -1 plus 0 is -1. -1 plus 1 is 0. 1 plus 0 is 1. And 0 plus 0 is 0. That's done. Now what we want also is for the entry below that leading 1 in row 2 to be a 0 as well, that -4 to become a 0. How do we get that to happen? It's 4 times row 2, because we're using row 2 here, plus row 3. Okay, that should do it for us. Let's see what happens. 4 times 0 is 0, plus 0 is 0. That's fantastic. 4 times 1 is 4, minus 4 is 0. That's just what we want. 4 times -1 is -4, plus 3 is -1. Man, I'm so hungry. I'm sorry. Okay, let's continue. Whew. 4 times 0 is 0, plus 3 is 3. No, I messed that up. Sorry, I'm on the wrong road. Okay, sorry. Get going again. That hunger pain threw me off. Okay. We did 4 times row 2. That's -1 plus 3 is -1. 4 times -1 is -4 again, plus 6 is 2. 4 times 1 is 4, plus 0 is 4. And 4 times 0 is 0, plus 1 is 1. Okay, I hope I did it right. Running out of juice here suddenly. All right, what we want next? We got a 1 here, 0's below it. A 1 is first non-zero entry in row 2 is a 1, 0 above and below. Fantastic. What we want in row 3, the first non-zero entry to be a 1. Unfortunately, it's a -1. But that's really easy to change. Change the sign of the whole row. Make that a plus, a minus, a minus, and a minus. Done. Okay, what we did there was minus row 3 becomes the new row 3. Okay, that's all we did. Just negate everything in it. Of course, -0 is still 0. Okay, what we want now is the entries above that leading 1 that we just changed to leading 1 to be 0. And that's going to be easy on both counts because you just add row 3 to row 1, and later we'll add row 3 to row 2. So row 3 plus row 1. Okay, that's going to be the next step. So we're using row 3, 0, 0, 1, -2, -4, yuck, -1. All right. Adding row 3 to row 1. Okay? So 0 plus 1 is 1, 0 plus 0 is 0, and 1 minus 1 is 0. Continue. -2 plus 0 is -2. -4 plus 1 is -3. And -1 plus 0 is -1. Okay. We got the top entry above that third row leading 1 to be a 0. Now we want the middle row entry above that 1 to be a 0. And again, you just add row 3 to row 2 this time. Okay? And that was the 0 and 0 is 0. 0 and 1 is 1. 1 minus 1 is 0. That's what we want. And then minus 2 minus 1 is -3. Minus 4 plus 1 is -3. And -1 plus 0 is -1. Okay. Now we have found our A inverse. That's this part right here. Before I do anything else, let me just check to make sure I didn't make a dumb mistake. And no, I didn't. It looks like it's right. Yeah. So, I hear a door opening, but I don't see anybody yet. Oh, there we are. No student showed up for class today, but I'll be out of here at 12:15. No, 12:45. Okay, it was the cleaning lady, not a student. Okay. Now, what we're supposed to do next is verify, confirm this by showing the A times A inverse is the identity matrix, and the A inverse times A is the identity matrix. Let me just do one of those. It doesn't really matter which. I'll write down A first and then A inverse, and we'll see if it works. Here's A, 1 minus 1, 0. 1, 0 minus 1, -6, 2, 3. Okay. So multiply that by your new A inverse, which is -2 minus 3 minus 1, -3 minus 3 minus 1, -2 minus 4 minus 1. I'll pause for just a moment here. I've got a student coming in. Sorry, I had a student come in to turn in some work. I took advantage to go down and get something to drink because my throat was so dry. But let's go on and we're only going to check it one way. They want you to check it both ways, but we just don't have time or space on this slide to do it. So this is a 3 by 3. That's a 3 by 3. So obviously the product matrix is going to be a 3 by 3. 1, 2, 3, 1, 2, 3, 2, 3. Okay? Now, first entry is the 1, 1 entry. So it'll be first row of A times the first column of A inverse. Later you'll do it the other way and it'll still work. -2 plus 3, that would be a +1. And then a 0, that'll be a +1. All right, good. Next entry is a 1, 2 entry. First row, second column, -3 plus 3, 0. That's 0. Next entry is the 1, 3 entry. First row, third column, -1 plus 1, 0. That's a 0. Then we'll do the 2, 1 entry. Second row, first column, will be a -2, 0, +2. Well, that's a 0. Then the 2-2 entry is a second row, second column, -3, 0, +4. That's going to be a 1. Okay? The next entry is the 2-3 entry, so it's second row, third column, -1, 0, +1. That adds to be 0. Then the 3-1 entry is third row, first column, -12, -6, +12, -6, that would be +6, and minus another 6 is going to be a 0. Okay? Then the next entry is the 3-2, so third row, second column, +18, -6, that would be +12, and then another -12 will be a 0. All right? And then the 3-3 entry is third row, third column, that's a +6, a -2, that would be a +4, -3, 1. Ding, 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 we have the identity matrix. That's what you need to have, that's what you've got to have if these are inverses of each other. And you can then do A inverse times A, you'll find it works the same way. Okay? If not, someone's made a mistake somewhere. Okay. Now, this process that we just did applies to any n by n matrix, A. Will be used to find the inverse of A if it exists. If it doesn't have an inverse, the process will also tell you that, and the next example will be that. And I thought it was going to be very similar to this, but it's not. So let's erase the whole slide. I thought maybe I could get by with just doing parts of it, but no. Erase the whole slide. And here is our new A. A is this matrix here, 1, 2, 0, 3, -1, 2, -2, 3, -2. Okay? We're going to adjoin that with the identity matrix. The same size, 3 by 3, so it would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, and then we start our row reduction. First thing we want to happen is a 1 in the upper left. So this A is now becomes AI. Okay? First thing we want is 1 in the upper left. We got it already. We don't have to do a thing to get it. So we're happy campers here. So we're going, next thing we want to happen is the entries below it to be zeros. Well, we got some work to do there. Not bad, but some. So -3 times row 1 plus row 2 will produce a 0 where that 3 is now. Should anyway. So let's proceed. We're using row 1, so we write it down. 1, 2, 0, 1, 0, 0. Okay, using row 1 the way it's indicated here. It's -3 row 1 plus row 2. So -3 times 1 is -3 plus 3 is 0. Ding, ding, that's what we wanted. -3 times 2 is -6, -1 is -7. -3 times 0 is 0, plus 2 is 2. -3 times 1 is -3, plus 0 is -3. And -3 times 0 is 0, plus 1 is 1. And -3 times 0 is 0, plus 0 is 0. All right, second row done. Okay, for now. We're going to do it more with it later. So sorry. I'm having trouble breathing. I was stopped up this morning when I was given the first class test. I don't know if that room was cold or what, but suddenly I just started sneezing and clogged up so badly and haven't gotten over it yet. All right, so what we want to happen next is the entry under that 1 in the third row to be a 0. To get that to happen, multiply the top row, because we're using that leading 1 there. Multiply the top row by 2, add it to the third row. So 2, row 1, plus row 3. Okay? So 2 times 1 is 2, minus 2 is 0. 2 times 2 is 4, plus 3 is 7. 2 times 0 is 0, plus, or minus 2 is minus 2. 2 times 1 is 2, plus 0 is 2. 2 times lost where I was. 2 times 0 is 0, plus 0 is 0, and 2 times 0 is 0, plus 1 is 1. All right. Now, before I do anything else, okay, like divide row 2 by -7 to make that become a 1, I just happen to notice that the first 3 entries in rows 2 and 3 are identical except for the sign. Okay? Well, what would happen if we just added those 2 rows together? That's a legal move, but what does that give us? Not using row 1, that's 1, 2, 0, 1, 0, 0. I can't write. Goodness, I can't do anything. Okay, now, we'll leave the middle row okay now. Normally we wouldn't. -7, 2, -3, 1, 0. Now, third row is add row 2 to row 3. What do you get? 0 plus 0 is 0. -7 plus 7 is 0. 2 minus 2 is 0. -3 plus 2 is -1. 1 plus 0 is 1. And 0 plus 1 is 1. I say 1 and write a 0. Okay. Hold the presses. Okay? There's no way this is going to become an identity matrix, not with a row of zeros at the bottom. This does not. That A that we started with does not have an inverse. Don't try to make it have an inverse. It won't. It can't. It will not. So therefore, hang it up. There is no way to get that to become a 0. An identity matrix, because you wind up with a 0 in that third column. Okay? Now you could have done other steps first. When you got into this step, this would have happened then. Why waste your time doing other things when you saw those 2 rows added together going to give you 0? No matter what you do, as long as it's correct, you're not going to be able to avoid that. So sure enough, that is, and I think they took it the same distance we did, and that's what they got. Yeah. Okay. All right. Now, and someone may be coming in. Yes, we do have somebody here today. Oh, 2 somebodies here today. Well, wonders never cease. Okay. Y'all are the first 2, and so far the only 2 here. All right, good to see you. Daniel and Muhammad. Okay. Now let me get set up for y'all. I just finished doing example 4 on page 66. So let me turn on the projector and ride too. I need to go get something to drink too. I was just, as soon as I finished this, I was going to. All right, that finished example 4. And what example 4 was, by the way, y'all weren't here to do it. We did an example with, I did an example with a matrix A. To find the inverse of matrix A, that would be this 3 by 3, you adjoin that with the identity matrix of the same size, and which is that. Then you start your row reduction. Now this has to be Gauss-Jordan row reduction, not just Gauss-Jordan row reduction. And what we did, we had a leading one there, fantastic, that's what we want. Then we wanted a 0 below it, both zeros below it, so we did the operations to get that one, and we did the operations to get that one. Okay? Then, before we did anything else, normally we would have stopped here and said, I want a 1 here, so you had to divide everything by -7. I really didn't want to do that yet, because I noticed this row, this column, these two, those two are exactly opposites of each other. So I just added these two together, and then you wound up with a 0, 0, 0, and then something else over here. Well, now the odds, the target here is doing this row reduction is so you can wind up with an identity matrix here, and then what's here is the inverse of A. Believe it or not, that's the inverse of A. But when you wind up with a row of all zeros, you know that this A did not and could not have an inverse. Otherwise, it would have been a 0, 0, 1 down here. And since it's not, there is no inverse. So that's what this problem showed. And I just completed it right before y'all walked in. All right. But you have to use Gauss-Jordan. This one, we didn't even get to do any Jordan part because we wound up with the row of zeros first. Now their statement here, using Gauss-Jordan elimination to find the inverse of a matrix works well, even as a computer technique for matrices of size 3 by 3 or greater. For 2 by 2 matrices, these are really small ones, you can use a formula for the inverse of a matrix rather than Gauss-Jordan elimination. And this is such an easy formula, don't even bother with Gauss-Jordan, okay? And here they're going to give a justification for it somewhat. I meant to hit this circle, okay? All right. For a 2 by 2 matrix, let's have A being a 2 by 2 matrix, A, B, C, D. I love it when they're all letters and not numbers. They're so much fun to do. Now, here's a statement. Then this A is invertible if and only if, IFF means if and only if, AD minus BC is not equal to 0. If that is equal to 0, it's not invertible. Okay? If AD minus BC is not 0, it is invertible. If it's not 0, then the inverse is given by, so the first thing you do is do that. And this is called, later, the next chapter we're going to be doing this, is finding the determinant. It's the product of the main diagonal minus the product of the minor diagonal. That's it. That's it. That is the determinant of this matrix. Okay? Now, if that determinant is not 0, then here's how you can get A inverse without doing any Gauss-Jordan elimination at all. Okay? Now, the first thing is you just calculated this, AD minus BC. Okay? And you found out it wasn't 0. And since it's not 0, you can put it in the denominator, can't you? AD minus BC. Okay? Now, you multiply that by another matrix, a 2 by 2 matrix, and here's how you get that 2 by 2 matrix. It's pretty simple. You just have to remember the steps. Okay? you exchange the A and D. Put the D here and the A there. The main diagonal elements, you just flip them. The off-diagonal elements, which are the other two elements here, you negate. So you make it a minus B and a minus C. So you exchange the main diagonal elements and negate the off-diagonal elements. Now this only works for a 2 by 2, okay? But that's the rule. All right, so let's do example 5. All right, here is matrix A. 3, -1, -2, 2. All right. Now, does anyone really want to do Gauss-Jordan on it? You could. First thing I do was flip the 2 rows, okay? Then divide the second row by, which now is the top row, by -2, and then you'd have a 1, -1. And then you reduce. But yeah, that's a little bit of work. And it's not too bad, but it's a little bit of work. But it's easy to do. But let's just see if this even has an inverse. What's the test? It's sort of like a cross multiplication, only with a subtraction. The product of the main diagonal, which would be 6, minus the product of the off diagonal. That would be a -2. Minus a positive 2 is -2. That's equal to 4, right? And 4 is not equal to 0. We are guaranteed this matrix has an inverse. Now, to write down what the inverse is, if it's not equal to 0, the matrix has an inverse. If it is equal to 0, it does not. That makes it a singular matrix. Okay? The what?
This test right here can only be used
2 by 2s. 2 by 2s. Okay, only. Okay? So, now you can actually just write down, in a sense, the inverse of the matrix. Okay, you start by 1 over 4. 1 over that determinant, whatever the determinant was. Of course, if it was 0, you can't divide by 0. Well, that didn't have an inverse, okay? So, write down 1 over 4, 1 over the determinant, and then you write down the elements, okay? And remember what I just said the elements were? Exchange the main diagonal. So make the upper be 2, the lower be 3. Okay? And then negate the other 2. Make that a 1, that a 2. Okay? And 1/4 of that would be 1/2, 1/4, 1/2, 3/4. But frankly, I'd just as soon leave as 1/4 out front. How's that? Okay? Now, because you could have left that 1/4 out front, I'm going to verify that A times A inverse is that A inverse, that is your inverse of A. And here's how I'm going to do it. Do the product between A and A inverse. Okay? This is, say again?
Why do you have 1/2 on the row 2 column? This is another divide.
Okay. I'm not sure I understand your question. Why, when you multiply this by that, you get that? Is that what you're asking?
Yes.
1/2, 1/4 of 2 is 1/2.
Yes.
Or 1/2.
1/4 of 1 is 1/4. 1/4 of 2 is 1/2. And 1/4 of 3 is 3/4. Right? Did I make a mistake there? No. Okay. All right. Now, how to check to see if these are indeed inverses of each other? Multiply them in either order. And it better come out being an identity matrix. Okay? But here's what I'm going to do. And this is legal in most states. I'm going to leave off the 1/4 here. Okay? I'll multiply that at the end. Is that okay? Okay, let's do it. So let's just multiply these two matrices together. I'm going to get these lines out of the way so they're not so confusing. Okay, and we're just going to multiply those two matrices together. Okay, A times A inverse. Well, that's going to be a 2 by 2, right? No question there, right? Right? Okay. So that's the 1, 1 entry would be the first row of this one times the first column of that one. That would be a 3 times 2 is 6, minus 2 is 4. Right? You do the next one. I'm sorry? 3 times 1 is 3.
Which two matrices are you multiplying by?
I'm sorry, I can't hear you.
Which two matrices are you multiplying by?
We're multiplying these two here.
Okay.
I'm leaving out the 1/4. I'll come back and multiply that at the end. In fact, I'll write it down here. Okay? Bless you. Okay, I did the first entry. You do the next one. 3. That's a 0. Fine. Next one.
You have
Negative 4.
and 4.
That adds a 0, right? And then the last one. Negative 2.
And then we have 6.
Negative 2 plus 6 is 4. And then multiply that by 1/4 and you get 1, 0, 0, 1. The identity matrix. There it is. Now, you really ought to do it the other way too. Multiply this one by that one, reversed. You'll get the same answer. Okay? If you did it right, and we did. So that to me is easier than Gauss-Jordan. Okay? Just check to see if it works by doing the determinant. If that's non-zero, you know it's invertible. If it's is 0, no it's not, you don't go any further. If it's non-zero, then take that determinant and put the reciprocal of that out front. The determinant was 4, so you put a 1/4 out front. And then, it's so simple, you reverse the main diagonal, put the 2, 3, and then negate the off diagonal. There it is. It's done. That is your inverse of a 2 by 2 matrix. All right? Let's do the B one. All right, to erase this one? Yay or nay? Okay. Okay, the B is 3, negative 1, negative 6, 2. 3, negative 1, negative 6, 2. What would you do first? Anyone want to do a Gauss-Jordan on this one?
I would check the thing first.
Second?
I would check if you have an inverse first.
I can't hear you.
I would check first.
Check first. Okay, let's check first. How do you check?
We got 6.
6 minus
Minus
6 is 0. Don't do another thing. This determinant is 0. It cannot have an inverse. Now, let me give you another reason it can't. And 2 by 2s are really easy to see this way. Notice that the second row is a multiple of the first row. Multiply the top row by negative 2, you get the second row. Those are dependent. They're not independent of each other. So no, that's not going to have a determinant. All right. Got it? Matrix B, that determinant is 0. So you have a non-invertible, which we also call a singular matrix. All right, now that we've played around some with inverses, let's look at some properties of inverses. Okay? We go till 12:45, right?
Yes.
Okay. So we've got a little over 10 minutes. Okay. Properties of inverses. Here's a theorem. Okay. A is an invertible matrix. Tell me something you know about A then. If it's invertible, tell me something. What's one thing you know about A?
It's not equal to 0.
It's what?
It's not equal to 0.
Okay, its determinant's not equal to 0, but if that's not a 2 by 2, that's not an easy thing to determine, okay? But what can you tell me about, for certain, about A?
Oh, nothing.
Those are right angles.
Square.
Square! A has to be a square matrix, n by n. That could be 14 by 14. Okay, it could be 7 by 7. It could be a 2 by 2 or a 3 by 3. It has to be a square matrix. You can't talk about inverting a matrix that's not square. So if you say it's an invertible matrix, it's got to be square. Got to. Okay?
So you can test all square matrix.
What's that?
So you can test all square matrix.
You can test them, but if it's not a 2 by 2, that test is very difficult to do. So you just go on and do the procedure. If it's a 2 by 2, do the test first. Okay. So if A is an invertible matrix, K is just some constant, positive integer, okay, not just any code, positive integer. Okay, positive integer. C, a not equal to 0, but any scalar. It doesn't have to be an integer. It doesn't have to be anything. It just can't be 0. Okay? Now, if those conditions are met, then here's the conclusion of that. The inverse of A raised to the kth power, remember K is a positive integer, okay, C times A and A transpose. All four of these things are guaranteed to be invertible. If A is invertible, its inverse, of course, is invertible. Its multiple is invertible. Its scalar multiple is invertible, and its transpose is invertible. All of those are. Okay? And in addition to that, these four issues. Number one, if you had A inverse, we know it's invertible, so it has an inverse, and if you take that inverse and do the inverse of that, what do you think you wind up with? If you do the inverse of an inverse, as long as it has an inverse, what do you wind up with? Where we started, A, exactly. Okay, so that's the first rule. The second rule, now this one we're going to deal with that K. A raised to the kth power, the inverse of that. Anyone want to make a guess of what this would be? Now they give some intermediate steps here which they don't really justify too well, but it's true. It seems like to me they just go straight to the chase, and I think I'm going to do that. That's equal to the same as A inverse raised to the kth power, which is A inverse times A inverse times A inverse. I shouldn't be using parentheses, but I just all the way up, you know, K times, okay, 3. So what this tells you, even though this -1 indicates an inverse, it's not really a superscript. It is superscripted, but it's not our normal thought feeling of a superscript. But still, you can count it as a superscript and exchange the two. Even though it doesn't stand for the reciprocal, you can still operate it like it did. Okay, number 3. If you have C times A and take the inverse of that, what you wind up with, now C is a constant, a non-zero constant, okay? Then the inverse of that would be 1 over C times A inverse, okay? So you reciprocate the C part, the constant part, and do the inverse of the matrix part. And then finally, number 4. If you had the transpose of A and we're wanting to take its inverse, what you can do simply, and I mean it's not all that simple necessarily, is do the inverse of A and then transpose it. And that will give you the same result. And again, the appearance is that -1, where it's just an operator saying take the inverse of this thing, you can actually act like it's an exponent and exchange them. It's a little bizarre, but it is true. Now remember, this only works for square matrices, invertible matrices. You can transpose a matrix that's not invertible, but this rule doesn't apply because there is no inverse for it. All right, now they do a proof for some of those. I'll let you figure out whether you want to do those or not. Okay. Now, they have a little statement right before they get to the discovery that I think is worth saying. This is going to our multiple matrices, that a raised to the kth power. Okay? Here's a little thing they say. Show that these properties, a to the j, I'm sorry, they put a little j, I put a capital J. Let me change that. Goodness gracious, my stomach is growling so badly. A to the j times a to the k, I think we've already shown this before, is equal to a to the j plus k. You can treat it just like they were exponents, okay? And a to the j raised to the k is a to the j times k. Treat it just like it is an exponent, okay? For any integers, j and k. All right. Now let's do this little discovery here. Hopefully it won't be too bad. We may not have time to get it completed, but let's try. Here's A, 1, 2, 1, 3. Here's B, 2, -1, 1, -1. Okay. It says calculate AB inverse. Seems like we've done this before, right? Maybe not. Okay. So first, let's do AB. What is AB? Can you even multiply them? Yeah. What size will it be? 2 by 2. Multiply them. See what you get. What'd you say?
5.
How'd you get that? Okay, wait. You may be misreading my thing. This is a 2.
Oh,
Okay.
it's 4.
4. Okay, let me. Oh, yeah. Okay. I wanted to, since that misled you, I wanted to make sure it was readable. Okay, so the first entry is a 4. Next. Second.
I'm doing
Negative 3. Yeah. Next. 5. Next. Negative 4. Okay. Now let's do the inverse of that. AB inverse. Before you do the inverse, what might you want to do? Before you try to calculate the inverse, should you do?
test it.
Okay, test it. What do you get? Say again?
-8. No, 16. I'm sorry.
Yeah. Negative 16.
We got 7
Plus 15, and that gives you a
No, that equals 1.
negative 1. Okay? So yes, it does have an inverse. So what's the first thing you write down about the inverse?
It's going to be 1.
Well, 1 over negative 1, which is negative 1, times.
We do AB.
What's that again?
We do the inverse of AB.
Okay, what's the rule to do the inverse?
So you multiply A.
No, not multiply anything.
Oh, yeah.
Ex-
You swap
Yeah, swap the main diagonal.
negative 4.
Negative 4, 4 down there.
Yes.
And then you do what?
Negate, so it's going to be
3,
negative 5.
negative 5. Okay. I think we're just about out of time, aren't we? It's almost certainly we're not going to get all these things done. Okay. Do you want to do those on your own? Do you want to come back and do those next time? Or do you want to just start on the example 6 next time?
We can start on example 6 next time.
Okay, don't mess with these. You're going to do these on your own.
Yes.
Okay, good. So we'll start with example 6 then next time. All right, let me give you, say again? Okay, what's the question?
I worked this one out,
Okay.
but I'm having trouble how to note it for x3. How will I note x3?
Usually you just give that a letter like T, a parameter T.
Okay.
Yeah.
So I can say x equals t. I mean x3
Yeah,
equals
x3 equal T, then x1 would be 2 minus 3T, x2 would be 6 minus 5T.
Okay.
And then everything has the same letter.
Okay, because I looked online. Some people noted it as free. Some people are noting all real numbers. So I wasn't sure what to notate it with.
Okay.
So
If you listen to this, it would have told you.
yeah.
Okay?
So we figure that out.
All right. All right. Going to go.